Alright, let's do this. Looks like an easy one to start the month. April Fools. And see how fast we can do this. Maximum value of an ordered triplet. You have a zero index array nums. Return the maximum value over all the triplets of indices I, j, k, such that I is less than j is less than k. If all such triplets have a negative value, return 0. The value of a triplet of indices is equal to the first minus the last times nums of I. Okay, the value of a triplet is using the indices within the numbers array at those spots. The difference times the value at the last index. Okay. So the maximum value over all triplets of indices. So okay, so I, j, k are just later elements elements in order, and you take the difference between the first two and multiply it by some last number. So like 12 minus 1 times 7. The value triplet 0, 2, 0, 1, 2. Yeah, 12 minus 1 times 7. Yeah. So that'd be 11 times 7, which is 77. Here it'd be 10 minus 3 times 19, so 1, 2, 4. And here obviously it's just 1 times 2 minus 3, but since there's nothing that is positive, then you just make it negative. You just return 0. Okay. Alright, seems simple enough. So the numbers is 100 in length, and each number can be 10 to the 6. This seems like n squared deal for each value, for each later value, for each later value to that. So I guess that's n cubed. Alright, let's try the n cubed. Simple n cubed approach. And we'll see if we need to optimize from there. So for each index I in the range of n, where n is the length of numbers, and then for each index j in the range of I plus 1 to n, and then for each index k in the range of j plus 1 to n, say value I is equal to index nums at I, value at j is equal to nums at j, and values at k is equal to nums at k. So we have an answer, and then we can say the answer equals the maximum of the current answer and the value I minus the value j in parentheses times the value k, and then return the answer. Alright, see how slow this is. This should work though. Alright, so pretty slow, unoptimized. Alright, how to optimize this? So for each value, what can be done is well, simple thing is you can always skip values of j that is smaller than values I because, or bigger than values I, because then you have a negative. So if you just optimize for if value of j is smaller than or bigger than or equal to value I, that's just not going to work. Because you can't subtract like 12 minus 13, get a negative number times another number, which is definitely going to be positive, and that's all just going to be below 0. What's going on? Try reloading the page. Okay, buddy. Happened here? 1 second. Right. Now I got logged out. How weird. So, yeah, so I'm gonna go ahead and try to not subtract something that's bigger than something that's smaller. Values. Whoops. Probably should do the if statement after I do the variable declaration. Alright. Okay, well, that obviously improved it. Still n cubed. There has to be a faster approach to this. So what you could do is, there's probably just a linear approach, like probably n. You could subtract each time for each index. For each index, you could subtract. How do you balance it out? You could possibly make an array of all the okay, what you could do is, since you're always multiplying by the biggest number after the second number, you could, for each index, determine what the biggest number after that index is, and then that'd be a one-time deal. So let's go ahead and say, so that would be using for the value of k. So determine biggest value after certain index for use to find optimal value k after certain index. So let's say biggest after is going to be an array. I'll go backwards through the well, it's going to be biggest after, should it be 0 initially? If I just make this into filled out. I guess I would like to probably go backwards through the array. Biggest. So for each index in the range of n minus 1 to negative 1 to negative 1, so that goes through all the indices in reverse order. The values can be the nums at this index, and then biggest after at this index. I'll say biggest starts out to be nums at the last value, and biggest after at this index is equal to the maximum of this value and the current biggest after. And what is the best way of approaching this? Okay. The biggest is going to be equal to the max of biggest and this current value. And then biggest after is going to be just the biggest. Okay. I think that works. And then this loops goes away. So for not every k, value k is just going to be the biggest after, big after this index. This index being index j, is that right? It's not quite right because the inclusivity is wrong here. The biggest after includes the value at the index value j. I think it needs to be the biggest after value j plus 1, index j plus 1. That would probably mean that this thing needs to be n plus 1, and then I need to make the biggest after at n, biggest after at the last one to be like 0, which technically is fine because if you are stuck where you're comparing j to something after that. Maybe this should be n minus 1. Let's go n minus 1. In which case you never, no, this thing is necessary. It needs to be j plus 1. But you don't really need to compare. J can't really be the last index in the thing, because then, in which case do you need to make this n plus 1? Guess you don't. Okay, I think that's fine. Biggest after -1 is 0. Okay, biggest after should be just times n. Don't go out of bounds, so j goes to n minus 1 rather than to n. And then answer is equal to max of answer and value I minus value j times value k. Now this is going to be n squared. Still probably not fast enough. Okay, so how to improve that? So not really a simple n squared approach anymore. So if you, for each index, if you're dealing with a bigger number than a later, for each index, let's say it was like 110, right? If it's a smaller number and then a bigger number, would you ever use the smaller number? So could you somehow determine that 1 is just not usable if there's a 10 after it? As long as the number after it is bigger than the number currently, and there's enough numbers after that, then you shouldn't be trying this current number at all. And if the number after it's smaller, then you should try it. Possibility. So for each value j, if value j, if value j is bigger than value I, and there's enough numbers after it, then there's no way that that you should be evaluating value I any further. So value j is bigger than value I. Does it matter if there's any number afterwards? Like, what if it's like 1, 10? So can you just stop when you see a bigger number? It's 1, 10. When would you care to not stop? Like, if there's one number after that, then it's just not possible. If there's two numbers after that, then you would want to use the 10. So I think you always stop if you see a bigger number. So I don't think this is continue. If you see a bigger number, then you should. If you see a bigger number or the same number, I think you just break. I think this value just cannot work. Can you skip to that bigger number? Yeah, I think you can skip to that bigger number because that means everything in between the current index, like 1 and 10, just would be smaller than 10 as well. It could be 1, it could be like 12, 6, let's say this is 100. Let's say, there was an array that's 12, 6, 1, 2, 7, and there's 1,000, 4, 6. Like, whenever you see 12 and you see stuff that's smaller than that, then there's a possibility that was part of the answer. But once you see 1,000, no, that's not true. Like, the answer could have been part 12 and then some combination of the stuff before here. But once you see 1,000, the 1,000 is going to be better than 12 as the starting number for any later options. So so the starting number is this a monotonic deal? So you have a starting number, you push stuff on the push stuff on the stack that are smaller than it. And then when you see a number that's bigger than it on the stack, then you can pop off the stack and have the answer be the smallest number up to that point times the biggest number up to that point. It's going too deep. So like do 12, you don't do any comparisons, or you don't do any calculations. So you 12 goes on the stack, 6 goes on the stack, 1 goes on the stack. And then if 2 tries to go on the stack, it sees that 1's on the other stack, so it's going to pop off the 1. When it pops off the 1, it does 12 minus 1 times the biggest value in the array after that. And that's your answer calculation. That's now 12, 6, 2. Do you care about keeping the 6 or the 2? Because you already have the 12. You have the 12. guess you care because otherwise you're doing the calculation each time. You need to know that's smaller than the previous one. So we do 12 on the stack, 6 on the stack, 1 on the stack. 1 gets popped off, 2 gets in the stack. As long as it's smaller, when does it not? When do you care to evaluate? Okay. Alright. This stuff is fine. Answer equals 0. Let's go monotonic stack here. Monotonic decreasing stack, and that's keeping track of things that are decreasing in value. So for each I in range n, actually, is it for each I in range n? So the value I, actually I think, okay, the value is equal to nums at I. While there is a stack, and the top number of the stack. Do I even need to keep track of the stack? So do 12, and then while something's smaller than 12, while you see anything that's smaller than 12, you do the calculation. And then if you see something bigger than 12, then you just reset your value I to that value. Okay, maybe this is, okay, maybe it's not even monotonic. So let's say there's a start value. And the start value is just the first value in the array. For each index in range n, in range, let's say 1 minus n. So if the value of this index, so nums at I, is bigger than the start value, bigger than or equal to the start value, and the start value is going to reset. Else, you just do the calculation. Answer equals max of the start value minus nums at I times the biggest number at this after this. Otherwise, the answer is just whatever the current answer is. I think maybe that's fine. Gosh. Okay. Answer 231. This thing returned 0. What's going on here? If the value is bigger than or equal to start, then the start equals nums at I. How could this possibly actually do anything? So I being 1, so it starts out at nums I is 3. 3 is greater than or equal to 2. So start becomes 3. And then next time it does the loop, I is 2. Nums at I is 1. So it's 3 minus 1 is 2 times the biggest number after this is. Okay, I think I just need to prevent this from going out of bounds. So how is this going out of bounds? It's going out of bounds because we shouldn't have I be anything bigger than the second index, so n minus 1, I think. Let's test the test. Let's do that test result that failed. Okay, that works. Oh, okay. So 42 expected output is 14. All right, fine. Let's do some printout. Let's print the current index, the start value, and the answer. Okay, so index is 1, start value is going to be 13 at that point because we reset it. And the answer is going to be 0 because there's no calculation so far. And start values, and then index is 2. Start value is still 13. 13 minus 6 is 7. 7 times 2 is 13 minus 6 is 7. 7 times 2 is 14. How to calculate 42? Start minus, biggest after I plus 1. I don't know how the other test cases worked when that was a mistake. Okay. Oh my god! Same speed as the last one. Fuck. Alright. Fair enough. How to improve this? So it's linear now, for sure. Finding the biggest values can be linear. And this is linear. I wonder. Everything's gonna be the same. I think maybe if I actually have a biggest after array, then if I go through interesting. I can go through the biggest after a certain index. I could get rid of the an if statement if I do a biggest after and a smallest and a biggest before. So for each index, I do the calculation of that value times the biggest number before it and the biggest number after it. Like that number times that number as the middle number and take the biggest number before it, subtract it. Is that faster? I mean, there's no if statements there. I guess the if part would be doing the max. Is that faster? This is pretty darn fast. Oh wait, maybe the print is actually slowing down. Well, the print slowed down a bit. I think that shaved off like 4 milliseconds. I mean, half off. So going back to the idea of creating a biggest before and a biggest after, because the middle number is going to be trying to find the biggest number before to use as the starting number to subtract from, and biggest number after to use as a multiplier. So yeah, but is that really, so the maximum, so keep track of the maximum, but then you still have this calculation of the maximum, and this is basically an if statement wrapped in a max function. And you still are doing that for every index, so let's see how that's any better. What was the actual? So there's something here. A lot of people got it, or I don't know, 20, 30% of people got it. 1 millisecond. So is it not using maximum somehow? Is it just a straight, or is it the way that I'm creating my biggest array? Can I create my biggest array, or can I not create my biggest array? Can I not create my biggest array? What if I on the fly it's either not creating some of these things or skipping over certain calculations that you know are worse. Like this is already skipping over nums of I is greater than or equal to start. So if the value is bigger than the previous value, so what if you did one pass to just create your descending values and don't do the calculation on those values until after the pass? Is it descending? Like, if you have 12, is it possible that 6 could ever be, so like, going back to the monotonic idea, is it like 12, let's say there's another number here like 500, 10,000, 751. So if I create a monotonic increasing stack, it'd be like monotonic increasing or decreasing. This should be monotonic increasing. So it's just avoiding all these calculations of this thing right here. But is that actually all that slow? So let's say you have like 12,000. So you have 12. And you see the 1,000. There shouldn't be a way that you can use 12 as your starting value anymore. And you see 4, 6, or 500. What if I kept both a decreasing and increasing stack? So I keep a track of the biggest number I see so far and the smallest number I see so far. Keep track of the biggest and the smallest number I see so far. Then that's the same as this thing. It's just the calculation here. 12. Put 1,000 on there. I do 12 and then put 1,000 and then put 12, 6, 1. So if you see it's decreasing. Could the answer be 12? You have to do 12, 6, 1. And then you only do the check once you pop something off the stack. If it's 12, 6, 1 and you see a 2, then you're going to pop the 1 off the stack, put the 2 on the stack. So say you have 12, 6, 1. The answer should be at that point like 6 times 1, which is 6. And then you have the 12, 6, 2. You see this 2, you pop the 1 off the stack, 2. Maybe you shouldn't even, maybe as long as the stack has 3 elements, I don't think you actually need to pop anything off. So 12, 6, 2 is now your stack. Then you have 12, 6, 7. But since you're going to pop off the 6, no, you don't want to pop off the, you don't actually want to pop off the 1 because it could be 12 minus 1 times 7, or 12 minus 1 times 6 times 2. So maybe there's 2 stacks, like there's a decreasing order stack and small, there's a decreasing stack and an increasing stack at any given point. Increasing stack and decreasing stack. So first number is 12. That's the same for both. There's just too many comparisons here. If you have 2 stacks, then you have to compare twice each time. Like increasing stack after the 6 is going to be the same, decreasing stack is 6. And this is going to be 1. And then when you have a 2, then the decreasing stack should be 2 actually, right here. And then when you pop stuff off, you do like 12 minus 1 times 2. But 12 minus 6 times 1 could have been a possibility, no? 12 minus 6 times 1. So it could have been like 12 minus 9 times 5. Oh gosh. This seems so fast. For each index in the range n, do you need to create the biggest array? Can you get away with creating like a single variable? Biggest after a certain number. Biggest after a certain number. You create a biggest after and a biggest before. Then create a biggest after and biggest before. Greatest, biggest after, greatest, biggest before. Then you'd have two. You still do answer because the max of I mean, start is pretty much the biggest before, right? If nums I is greater than start, then start. This is the biggest before. And if it is the biggest before, then just ignore the calculation. I guess. And keeping an array for that doesn't really solve anything. And if you have the biggest before, if you have nums I, start minus nums I, so you automatically do the max calculation if you have the biggest, if you don't have the biggest before. So you automatically do it. Can you not automatically do it? Can you somehow figure out that you should be skipping this one? Because maybe there's a smaller number after it that you want to subtract by. Alright, I just don't see it. Alright, I think this is as good as I'm gonna get. Okay, I mean, it's pretty darn good. It is linear. Can't imagine it being like the difference between my solution and some other solution is probably just the fact that somehow they got rid of an operation within the for loop, but the for loop remains linear almost assuredly. Summary. This is shortcutting calculation by two things. This is one is determining the best index j by creating an array where for each index the largest value after that index is stored, since that will be guaranteed, that will have to be used for the calculation. And then the other thing was determining the best index I, which will always be the biggest value up to any given index. This might be a little confusing. I think maybe this should be called index j, because what I'm really iterating here is index j within the context of what's defined. So for index j, start is the first index, which is index I pretty much, or the value of index I. Start is this. I think this still works. Oopsie daisy. Order of operations. I guess I should call this. Oh, yeah, this is actually index k. Returning the best index k. Yeah, index k being the last multiplier, index j being the middle term to subtract by. Alright, time complexity here is just going to be open to create the biggest after array, and also to iterate over to determine the best. Index j includes all the calculation. Because once you know what the best index j is, then you already know the start is you're giving the first value to subtract from, and then big after giving the last value to multiply by. Basically, let's say there's a little n here to create the biggest after array. I wonder if you didn't have to create this array, is there a way to have done this without? Well, there might have been a way to create this without this array. I don't see it though. This is really, really important. I don't see how you would on the fly keep track of that information. Not without some complicated hoops. Alright, well, that was easy. Bro, check this 3-liner. What was 3-liner? Are you gonna give the 3-liner? Okay.